In this example, I'm going to consider a locomotive or train that's pulling 15 cars behind it. And I want to know the ratio of forces of force between cars 3 and 4 to the force between cars 7 and 8. Let's think about what's going on here. I'm going to say that each car has a mass m and that the locomotive is moving forward with some acceleration. In fact, if you want, we can assign a number to it. Let's say 6 meters per second squared. Now I want to know, how hard does car 3 have to pull on car 4, and then by Newton's third law, reaction force 4 on 3, compared to how hard does car 7 have to pull on car 8. To do this, I want to think about what each car knows and what the locomotive knows. Now obviously they're not people, but I'm going to personify them a bit. The locomotive is attached to car 1. Now it's obviously pulling all the cars behind it, but all it knows is it's attached to car 1. Let's take that thought and move down to the last car. Car 14 is attached to car 15. And we know that there's a force between them, so 14 is going to pull on 15 because 15 has this acceleration of our system, 6 meters per second squared. We know that 15 is accelerating with that. And if all of our cars are identical, car 15 has a mass m. So the force that 14 has to put on 15 to pull it forward is ma. Now let's do that again for car 13. Well, 13 is going to pull forward 14. But it's also, because 14 is attached to 15, pulling forward the mass of 15. So as far as car 13 is concerned, it's really pulling forward one big car of mass 2m. And so the force between 13 and 14, because remember everything is accelerating at 6 meters per second squared, will be that big mass 2m, and it's accelerating at 6 meters per second squared. And then we can do it again for car 12, and so on and so forth. But we're asked about two in particular. First, car 3 and 4. So to answer the question for 13, I looked at it and said, well, there are two cars behind it, and 13 has to pull forward the mass of both of those. So if I want to know about the force between 3 and 4, I'm going to look at car 3 and think about how many cars are behind it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So car 3 is going to apply a force on car 4 that can accelerate 12 of those masses at 6 meters per second squared. So this would be 12 masses of cars times 6 meters per second squared. What about cars 7 and 8? So if I go to 7, it has to pull on 8, which is in turn pulling on all these masses behind it. And there are 1, 2, 3, 4, 5, 6, 7, 8 cars behind 7. So that would be pulling forward 8 masses at an acceleration of 6 meters per second squared. The 6's are on top and bottom of fractions, that goes away. The m's for mass go away. We're left with 12 over 8, which is about 1.5.